This is the Part 3 video podcast for Chapter 17 about groundwater measurement. Now we're going to move to more complicated concepts, understanding groundwater flux and how to measure aspects related to groundwater flux. We're going to have to look at this at both the local scale as well as at the scale of a whole aquifer. This is also a good time to remind you that the point of this class is not to provide you with all the understanding of the theory of how water moves and these different components throughout the course, but to really be a capstone, a refresher of what you've learned in other classes, and then really focus on the field methods that you need in order to take that theory and translate it into practice in terms of measurement. So with that in mind, we can now turn to the basic understanding of how water moves through the ground as explained by Darcy's law. To convey this understanding, I'll present the simple experiment. Imagine a cylinder or tube that's filled with porous media, in this case sand. I apologize for the quality of this graphic, but I think it's sometimes simplicity is a trade-off with quality, I suppose. Anyway, here we have sand, and it has a cross-sectional area A, which is the area of a circle. The flux through this is given as Q, so it's going to be flowing from the area of high pressure to low pressure. To get things started, we're going to have a water reservoir that's going to be maintained at a constant elevation or head, which is shown up here. And the water is going to be allowed to go down. Now, as water goes down, the water level won't. The water level is going to be maintained by a constant flux that will keep it just at the right level. Similarly, we're going to put another level here that's going to be connected to the bottom. So that creates a hydraulic head at the downstream end. And that is similarly going to be maintained by, in this case, by having a spill off so that water will be kept at this level. So we can look at the head at location 1 is equal to the elevation above the datum plus the pressure of the water relative to that datum. And in this case, we're going to be measuring it not at the reservoir, but right at the inlet of our sand porous media cylinder. So here's the water level in there. So H1 is Z1 plus P1 over gamma. And then at the downstream end, we will similarly have a little test well that will tell us the head at the downstream end, Z2 plus P2 over gamma. And the change in head is the difference between those two. You can imagine, and I've sort of said this before, that water flows from areas of high pressure to low pressure. So this is what's driving the water through this experimental setup. And our goal is to figure out what is Q, the discharge. Now, if this was a river, we know that because gravity is driving the flow of water, that the steeper the slope, the higher the velocity, and therefore the higher the discharge that can be moved. Well, it's no different here, except here the slope is expressed by this dH over the length that it's moving, just like how slope is the change in water surface elevation in a river, which is also a hydraulic head. So we have a dH dL. Now, it's a little bit different because the water surface elevation in a river also reflects the velocity head, whereas the velocity head here would be really, really small. But still, it's essentially the slope and head that over the length that this is flowing. So Q is proportional to the slope dH dL. And of course, the larger the cross-sectional area, the more flow as well. So that's there too. So if we wanted to continue this analogy with reference to a river, we could then say, okay, well, what are some of the other factors that go into affecting discharge? And you may remember from Manning's equation that it's going to also be a function of the resistance to flow. And that is expressed here by this parameter K, which is the hydraulic conductivity. Hydraulic conductivity represents the ability of the porous media to sustain the flow through it at a given level. So if we look here in terms of units, dH/dL is unitless, just like slope. Cross-sectional area has units of length squared. So to get a flux in length cubed per time, this has to have units of velocity. So hydraulic conductivity is the characteristic rate in units of length per time at which sediment pores permit liquid water movement. If the material, this porous media, is sedimentary, like an alluvium or colluvium, then it's largely going to be governed by the grain size distribution and the packing of that material. If there's organic matter in there or cohesive material, then it could be different. And similarly, if it's not sedimentary at all, but it's a hard rock, then it also is going to be quite different. And it's going to be governed by the nature of the fractures or solution, caverns that are present there. Also, you can see that the hydraulic conductivity in units of meters per day has dramatic variation. It goes from 10 to the minus 8 up to 10 to the 4th. So that's 12 orders of magnitude. And you can imagine that that would be very hard to precisely estimate. And it's a variable that groundwater prediction would be highly sensitive to. Another confounding aspect for this experiment would be if we didn't use well-rounded sand, but if we used a very platy material. Now, if I have a perfectly horizontal cylinder, so I'm not on a slope anymore like it was in the original case, but I have a horizontal media, and I have platy material designed that it's going across, and then the gray, it's not empty space, but a finer matrix of material, say with more rounded particles. I can impose a head on the left side with this hydraulic head up here, and I can have a hydraulic head on the right side here, which will induce a flow according to that gradient. Because the water is being put in with a horizontal gradient, it's going to move through here relatively horizontally, taking advantage of the platiness that's present. However, if I now shift the water so that it's coming from the top, like infiltrating in, and I have my hydraulic gradient from top to the bottom, now the water meets extra resistance because it can't just push in a straight line through. It has to take a tortuous path around these platy particles, and who knows where it's going to end up. So this is what we call an anisotropic porous media. Isotropic would mean it's the same in all directions. Anisotropic means that it's different. So there are some more terms to learn as far as groundwater hydrology. An isotropic aquifer is one in which the hydraulic conductivity is independent of flow direction. An anisotropic aquifer has different values in each flow directions, and that could be three-dimensional, not just two-dimensional. For most aquifers, vertical hydraulic conductivity, so the rate of like an infiltration or lowering, is much smaller than the horizontal hydraulic conductivity. And the hydraulic conductivity and flow pathways primarily take their leave based on the geomorphic and sedimentary processes that filled that ground if it's a sedimentary system. If it's not, if it's a geological one, it may relate to the fracture structure, or the earthquakes, or plate tectonics, or whatever's driving that hard rock setting. So for example, we live in the Central Valley here at UC Davis, and the Central Valley has, like 1,000 meters or more of alluvial fill over a very long period of time. Well, that fill, it's not just a pile of sand, right? It's structured based on the history of the rivers flowing through that valley. And rivers can be braided, anastomosing, avulsing, or just simple meandering. And each of these leads to a characteristic three-dimensional structure when you look in cross-section. So, for example, a meandering river might lay down a very well-defined sand lens, which is because sand is what is actively carried as bed load in a river. That's where you have the highest energy taking place during floods usually. And so you have the coarsest material. As you move away from the channel, it gets finer and finer. And then every now and then, the river may bust out during a flood and evulse to a different part of the valley, and therefore start a new channel and lay down different lenses of sand. So you can see that there are very strong preferential flow paths where water may want to go across the valley, but once it hits one of these sand lenses, it's going to flow much faster moving along it and in it than it is trying to go across it. And these systems can be different depending on the grain size of the material and the shape of the rivers and the bed load, water, and other things. You may remember from, I think maybe it was the stream assessment lecture, the lanes diagram that I showed you, which looked at the relationship of the variables that govern things like this. So this is an important process to understand for what's governing hydraulic conductivity and preferential flow paths. Here's an example of a reconstruction of the three-dimensional pattern of hydraulic conductivity in meters per day. Low is blue and high hydraulic conductivity is shown in red. Whether this is done from wells or remote sensing methods, the important thing to understand is that it is a highly variable property of the subsurface, and so one of the jobs of a groundwater hydrologist is to figure this out. Here's a simple experiment that you can do, pretty similar to Darcy's experiment, but done in a laboratory setting. So in this case, we're putting in a hydraulic head in the cylinder on the left, and we're actually introducing that into the bottom, and then we're allowing the water to run up through the top and down through. And so you can actually calculate or observe the rate at which water is leaving the system based on how fast it's accumulating here in the cylinder, and that also could be logged with a computer. So this is just an example. This can be done for both saturated as well as unsaturated conditions, and this is done as part of Jan Hopman's Soil Science 107 class. Another case where it's interesting to consider how we would measure groundwater is through what we call losing or gaining streams. A losing stream is one in which you have a relatively dry landscape and you have a storm that produces water over that dry land. As water runs down the river, it actually is absorbed or infiltrates into the ground so that the amount of discharge decreases down the river. If you had tributaries coming in, maybe it's going to add more water, but the net effect is a loss considering the relative to the sources. If you lose so much, if the system is so dry that the water table is actually disconnected, not only are you losing water, but we call the river itself, the river is basically creating infiltration that is going to pond the water table up higher than the surrounding level. And so we would call that perched water table relative to the surrounding water table. The technology that you can use to assess whether a stream is gaining groundwater from discharge or losing water as groundwater recharges to the water table is called a streambed seepage meter. Now, before showing this, another thing you can do, of course, is if you're really good at stream gauging, you could use the velocity area method at an upstream location and the velocity area method at a downstream location. And the difference in discharge will primarily be due to what's going into the ground. And that's true for gaining streams too. If you're gaining water, the difference in discharge over 10 kilometers or something like that would reflect that gain. You just have to be mindful of any evapotranspiration losses as well as any tributaries that are coming in. However, if you want to see the gaining or losing directly and not just through a mass balance, then you can use this streambed seepage meter. Essentially what you're doing here is you're taking something like a 55-gallon drum where it's open on the bottom end and it's sealed on the top. You're pushing this into the riverbed, and what we have then is we have a bag of fluid in another container. Okay, this looks a little bit confounding the way this is shown here, but this is actually not in the bed, whereas this main one is in the bed. One thing you can think of is if you think of like the saline bags that are used in hospitals to rehydrate a person, imagine a bag like that attached to this tube where it's not completely full, but it's like half full. and you know exactly how much water is off in this other container. What happens is that if water is being gained to the river from the subsurface, the water is going into this bucket, then the water will go into the bag. And you would see the bag actually inflating over time as water goes in there. Alternately, if it's a losing stream, then water inside this sealed area will be infiltrating down into the subsurface, and water in your bag will diminish. So this is just a little bit fancier version of it with a larger wine bladder, or like I said, a large IV bag, and you're either gaining or losing, and you just have to be pretty mindful about how to set this up. But effectively, you're seeing the water as it goes in or out of the ground. And this is not something that you only use in a stream, but you could use this in a lake. So if you wanted to know if Lake Tahoe was a gaining or losing, you could put these kinds of meters at 50 feet down anywhere really in the bed you want. And you could see whether you're gaining or losing. Okay, the next important idea that ties to this groundwater flux that's really important is porosity. Now, porosity is also going to be important when we look at the vadose zone, but I want to start bringing it up now because it's going to be relevant to understanding the aquifer scale ability to store water and pump water out. So porosity is defined as the percentage of a soil or rock volume that is not occupied by solids. It affects the ability of water to flow. I mean, the larger and more pores you have, then the more water can be stored and the faster it can be moving out. If you have very fine pores, then you do get a surface adhesion that's taking place, and you also have water held back against gravity by capillary forces. So surface tension and adhesion are really important here. If there are very large pores, then water is going to move freely as a result of gravity. Of course, there's more again related to the size, shape, and connectivity of the pores, whether they're connected or isolated. We're only interested in the connected pores that have the ability to give up their water, which we'll call effective porosity. And here are some images showing the grains as the bigger particles and the pores in between those. The pores, if they're filled with finer material, then the pores are not are only just the area where there's no solids. So how does porosity link to groundwater concepts? Well, it has to do with the ability of the ground to give up that water. We'll go into more depth about the suction that soil can put onto water when we talk about the vadose zone, but it's important to understand that adhesion and capillary forces can hold onto water, and we call that specific retention. Specific retention is the water that's held by those forces. Specific yield is therefore the water that we can pull out of it without having water kept behind by the retention. And it's often given as a percent of the total volume of the medium that's present. So for example, if you have a coarse gravel, it's going to have a relatively low overall, water content, right? Because so much of it is going to be composed of solids. But of that pore space, the vast majority of it is going to be effective pores that are all interconnected, and a large amount of the water is going to be able to be removed as specific yield. In contrast to that, look at clay, right? Clay may have a lot of very small pores, but you have a lot of adhesion and capillary forces, so very little of that water can be drawn out of it. Peat is sort of a weird mix of these things. It can have a ridiculously high water content, but a lot of that is inaccessible because of the cohesiveness and lack of basically just the ability of adhesive forces and capillary forces to retain large amounts of that water due to having very fine sediment and fine organic matter effectively acting as sediment as well. So with these ideas, that leads us to what's called the storage coefficient. The storage coefficient is the percent volume of water released from an aquifer per unit volume of decline in water table. So what does this mean? Okay, what this means is you're pumping away, you're pumping and pumping and pumping. How much water are you getting for all that effort? It turns out that for an unconfined aquifer, you get a very different amount of water per unit of drawdown that you do for a confined aquifer. In an unconfined aquifer, you're creating a water surface slope. The water is literally flowing down a water surface slope just like a river. So here you can see a water surface slope that's there, and therefore you can actually draw out a lot of water. And so the specific yield of water that comes out is anywhere from 1 to 40% of the water. So, again, depending on the grain size, texture of that sediment, you can draw out quite a lot. However, unconfined aquifer water is usually, fairly contaminated, right? It's pretty close to the surface, so whatever is going in is going to be there to contaminate it. An unconfined aquifer is going to be deeper and it's going to be isolated, so unless the source area is subjected to contamination, then this is your really clean drinking water. But the problem here is that in unconfined aquifer, the water isn't actually flowing down by gravity. Because remember, the unconfined aquifer doesn't actually dewater. Instead, what you have is a pressure gradient or a hydraulic head gradient, and the water is moving from an area of high pressure to low pressure. In the case on the left, water is literally flowing down to the well. It's laterally and vertically. In the case on the right, the water is flowing horizontally from within the confined aquifer to the screened interval of the pump. The water surface, or the hydraulic head gradient, is there and that's sloped, but the water itself is not. So here are some basic concepts to think about to understand this. The smaller the storage coefficient is, the less water you get out per unit of change in hydraulic head. So you're pumping really hard, you're pulling really hard, but you're not getting much response. And we call that a really stiff system. In an unconfined aquifer, you can get a lot of water moving, and as a result of that, water can be flowing from a much larger area, which means that the change per unit location is a lot less. So neighboring wells will show much less sensitivity for an unconfined aquifer than a confined one. Okay, so now we want to scale up to the idea of the transmissivity. So how fast does the water actually flow through the whole depth of the aquifer? This is basically, we take the hydraulic conductivity at a point and integrate it through the aquifer thickness. So the transmissivity equals hydraulic conductivity times thickness. And here's just some reference values for what those look like. Gallons per day per unit foot. Now this is where it could get a little ugly for you. I'm showing you some really tough math. But if you've taken a groundwater class, you've already seen this before. If you haven't, don't panic. I'm going to give you a very simple explanation for what these are showing. Let's take the equations on the right. Okay, let's say you're just looking across at the ground and you want to know, where is the water table? That would be the equations on the left. Okay, the equation on the right, you want to know, where's the hydraulic head? For if you were to put wells out there, how high would the water rise in those wells? Which again isn't the same as the water table, but is the hydraulic head gradient. And so what this shows is the hydraulic head at any location across the land. So hydraulic head, how does that change, or what's the gradient of that in the x direction and the y direction? So this shows the two-dimensionality of the land surface. And how does the hydraulic head change through time? So how the hydraulic head at any location change through time is proportional to the distribution of hydraulic head in space. And it's also a function of these two parameters that have already been defining the storativity and the transmissivity. In the case of the unconfined aquifer, it's the specific yield and the transmissivity. Now, the only difference between these two equations that you see here is that we have an h squared instead of an h. Without going through the derivations and without expecting you to learn those derivations, it basically has to do with the fact that aquifer thickness is varying in space in an unconfined aquifer, so we have to carry through that thickness as a variable and not just treat it as a constant the way we can pull it out over here. So that's all I want to say. If that doesn't sound very satisfying, then my advice is to take the full groundwater class and have the joy of solving for these equations, which it really isn't that hard of a derivation, but it's just something you'd have to go through. And as graduate students, that's definitely something that you should see. In any case, the purpose of these two equations is to allow you to predict the hydraulic head anywhere across the landscape. And all you have to do to know that are any inflows or outflows, of course, anything weird like that. But within a closed system, you just have to know the storativity and the transmissivity that's present there. And of course, you have to have some sort of boundary condition. So at the boundary, what is the hydraulic head? And again, are there any inflows or outflows? So this is a groundwater model that helps you to see the hydraulic head distribution and therefore helps you get a groundwater flux. In order to use this model, the parameters that you need to calibrate are storativity and transmissivity. So how do you get those at the scale of a whole aquifer? It's not just go out and do some seepage meter tests or hydraulic conductivity soil tests with some soil cores. You have to like warp, you have to interact with the whole aquifer. And the way to do that is with something called a pumping test. With a pumping test, you use one or more wells to pump water out of an aquifer, and then you see how does the hydraulic head field change as you move away from the pumping well by looking at different observation wells. So that's like a single pumping well, multiple pumping wells radially distributed away from that. And based on those observations, you can estimate the storativity and the transmissivity, and that's beyond the purpose of this class. What you need to know for this class is that you use pressure transducers. You set it to logarithmic sampling through time, so that you're sampling like every second initially, then maybe every minute eventually, and every hour, and then once a day. And you can see how the drawdown changes through time. So aquifer pumping is an example of model calibration. And then if we wanted to test this equation, we could put it into a computer model and use observations of the hydraulic head from the first video podcast to go around and see whether the predicted heads are matching what the model, the observations are showing. This would be covered in Professor Fogg's HYD 146 class. So we're not going to do a pumping test here because that's taught in another class. So this concludes this video podcast. There are 3 parts to it. What is hydraulic head? How do you measure it in a well? Then we covered the aquifer attributes and pressure transducers with strain gauges. And then we looked at a whole bunch of stuff at the aquifer scale to understand groundwater flux locally in losing streams, so stream groundwater interactions. And then taking the equations that predict the spatial pattern of hydraulic head and seeing how, as field hydrologists, we have to measure the storativity and the transmissivity to be able to use those models.